Hey guys, what's up? So today we're going to continue with running water erosion and deposition, being that it is probably the most dominant force of erosion and deposition on the entire planet. Please make sure you're taking notes. This stuff will be on your quiz that is this Thursday, so make sure you are paying attention to that. Reminder, you will be having your test next Tuesday or Wednesday. Not quite sure, got to see how the lessons turn out timing wise as to which day it's going to be. We're leaning more towards Tuesday, but we're not sure. You also have a quest that's up on Test Wizard. Make sure that you guys are doing that. That is due on Monday, 8/25, same as everything else. And without further ado, let's go. All right, so how does the stream actually erode? Well, streams are going to erode primarily through the actions of abrasion and dissolution. Now, what does that mean? It means they're going to lift up those loosely held particles, okay, through these two processes. Now, let's go over them quick. Abrasion means that you're getting hit by smaller little particles. We use the example of sandblasting when we were talking about this with wind erosion. Well, water carries little bits of sand and stuff like that, and so it's going to chip away at the riverbed and lift off pieces that get chipped away, okay? It's also going to dissolve certain liquids. Why? Because water naturally has this property to kind of make things dissolve, but then there can also be other things in the water that help certain minerals or certain ions to leak out into the water. Okay, now that process of abrasion is going to happen constantly. Why? Because the water is constantly flowing. So is this process of dissolution. Now, the stronger the river is, the stronger the currents in the river, the easier it is to lift particles, and the bigger the particles you're going to lift. So, for example, if you're looking at the picture in front of you now, you can see this river is cutting a path through these rocks. It has sawed its way through these rocks, and it is slowly eating away at the rocks. You can actually see right in the very front of it, you can see almost this little V-shaped curve. What's going on there? The river, as it flows past, is chipping away at the rock there, and it's lifting up pieces of it by abrasion and by dissolution, okay? And if you look at the picture now, you can see one of the side effects of stream erosion. One of the ways that you can tell if a stream was flowing over something is it has this tendency to smooth out the rocks, a tendency to make them very round and very smooth. In fact, one of the building materials that you may find, your parents may have used it in a bathroom or a kitchen, is something called river rock. River rocks are these incredibly smooth rocks. They almost look like eggs. Sometimes they're flat, sometimes they're very smooth, but water has this tendency to smooth things out. It gets rid of the sharp, jagged points that you get on rock, and there's this tendency to make them much smoother. Why? Because they're constantly getting blasted by the smaller little particles that are being carried inside the river. All right, so now that we're talking about the stuff that's actually getting carried by the river, what do we call that? Well, we call the transported material in a river or stream the stream's load. It's the amount of stuff that it can carry. Now, this material can be carried in a bunch of different ways. It can be carried as dissolved ion, suspension, or bounced and rolled. Now, what does that mean? Well, if you look in the picture in front of you, you can actually see this. Okay? At the top of the picture, you see where it says particles in suspension and ions in solution. So what does this mean? This is the very, very light, tiny little particles, sand, silt, and clay. If the river is moving fast enough, these particles just float in the water. As the water moves, the particles move along with it. The ions in solution, we talked about this when we talked about chemistry a little bit. Remember, we said that when an element gains or loses an electron, it can become an ion. Well, these ions can dissolve in water. This is what you find in Gatorade, for example. This is what you find in salt water. Okay, these are dissolved ions, and the solution is the water. Well, that's exactly what happens here. As the river weathers the stream bed below it and the walls of the river alongside of it, it's going to add these ions. These ions are incredibly tiny, and so they can just be kind of carried and floated along the river. But when we look down at the bottom of the picture, you see the larger rocks down at the bottom. The larger rocks down at the bottom are going to roll, or they're going to jump. Remember that word saltation that we saw with wind erosion. And so they're going to get jumped and pushed and roll along the bottom. And as all this process happens, they're slowly going to get rounded out, which is what we were just talking about before. All right, so the next concept we're going to talk about is what we call a stream's competence. And a stream's competence, basically, we're talking about what's the biggest size particle that a stream or a river can carry. Okay, and that is ultimately identified or determined by how fast the stream is going. Now, the easiest way to do this is to look in your reference table. If you look on your reference table on the same page as the rock cycle and the igneous rock chart, right in the upper right-hand corner, you will see this chart. Okay, this chart is the stream velocity chart. Okay, and this chart, and I actually have a slightly better one where it's color-coded and a little easier to follow. Okay, so make sure you open up your reference tables to that. Okay, this chart, if we look down at the x-axis here, you see stream velocity. Now, the numbers are a little bit weird because they're trying to give you an idea of all the possible velocities. The stream velocity is in centimeters per second. So if you look, the lowest velocity would be over here at 0.01. You cannot have a velocity of 0 because then your stream's not moving. Okay, so this would be your lowest possible velocity, and then over here you have a stream velocity of 1,000 centimeters per second, which is like 10 meters per second. Okay, on this side, on the y-axis, you have the diameter of the particles. Once again, going from 1/10,000th of a centimeter all the way up to 100 centimeters. Okay, and in case you were wondering what those are, on this side of the chart, this axis just lists the type of particles that you have. So clay particles would be anything from 0.001 to 0.004. Silt is anything from 0.0041, let's say, up to 0.006. Sand is everything here, and pebbles is everything here. Cobbles are here, and the largest particles are boulders. Okay, so if we're trying to figure out what a particular stream can carry, you have to cross-reference it. So how do you do this? So you follow the line right here. Okay, and so if we tell you that a stream has a velocity of 0.1, what you would do is you'd go 0.1 and you go up until you hit the line, the curve. And what that tells you is that this point right here is the maximum load that that particular river or stream can carry. Now in this case, you see it's particles right here. Okay, so what's the biggest size particles you could carry? Silt. So you could carry silt and clay, but you could not carry sand, pebbles, cobbles, or boulders. Okay, so anytime you're given one of these things, you just go until you hit the curve. Now, let's say a question gives you the particle diameter and you want to find out what is the river speed that you need to carry that particle. Let's just say I told you you have a 1 centimeter particle or 1 centimeter pebble. So you'd see 1 centimeter diameter pebble. You'd go across till you hit right there, and then you would go straight down right around to about 50. So your river would have to be traveling at 50 centimeters per second in order for you to carry a 1 centimeter in diameter pebble. This chart is used on a lot of different questions. You're going to get it in homework tonight, so please make sure you're paying attention to this chart. All right, so when we're talking about rivers and streams, they tend to form the most common landform that we see on Earth, which is called a stream valley. Now, there's two general types of stream valleys. There's the narrow valley, which is usually formed by what we call a young stream. We'll learn more about that in a minute. And these tend to be very deep. They tend to be very V-shaped. The water tends to flow very rapidly. The reason is because as the water flows across the bedrock, it almost saws its way into the bedrock and makes this very deep pointed valley. Okay, it works its way down towards what we call the base level being the rock that is the most resistant to weathering and erosion. Okay, a lot of times these are the rivers that you're going to find waterfalls and rapids and things like that. The other type of stream valley is what we call a wide valley or a mature river. Okay, these tend to be much wider, literally like the term implies. There doesn't tend to be as much energy directed towards the bottom. Actually, most of the energy tends to be directed towards the side. And so what you're going to tend to get with these guys is a more rounded bottom, not as sharp or pointed as a bottom. And a lot of the weathering and the erosion is going to tend to happen on the outer banks of it, and not so much weathering and erosion happening on the lower levels, on the base level. That's not where you're going to get most of the erosion. In fact, you're going to get more deposition in those areas than you would have gotten erosion. Okay, and you can actually see that in these three pictures that you see before you. The top picture represents what we would call a youthful stream. Okay, you can see it's sharp, it's V-shaped, you don't have a whole lot of stuff going on, maybe a couple of tributaries and things like that. The mature river is going to tend to have more things like floodplains, and it starts to wiggle a little bit, which we call meanders. Remember, we talked about that yesterday. And a older river, the oldest of the rivers, okay, is going to tend to have a very, very big sweeping. It has a snake-like appearance. The floodplain, which is the area where you get when it floods and it deposits all the sediment, is absolutely enormous. Okay, now as rivers develop, rivers are going to develop, and they're going to go through this process of being what we call a young stream or a young river, a mature stream, and then eventually what we would call a old river. Now, if you look at the picture, once again, you can clearly see this in actual terms of what one actually looks like. The picture on the upper left-hand corner, you see that nice V-shaped valley. You see there's not a whole lot of depositional features around the river. There's no meanders, there's no bends. The mature river, you see it's starting to bend. starting to twist. It's get that more snake-like appearance. And then all the way in the bottom right-hand corner, you see the old river. And the old river has these huge, it's incredibly wide, and it has almost these little offshoots that happen. Now, an individual river can actually go through all of these processes in its lifetime. The diagram that you're looking at right now, you see a river up in the mountains that starts off as young with a nice deep valley. Mature, where you can see the valley is widening out and flattening out a little bit, and the old once it gets to a very flat stage. Typically the gradient is going to also determine this. If you're high up in the mountains, you tend to be young. If you're on flatter plains, you're going to tend to be a little bit older. Now, one of the major factors of a stream valley is what we call a floodplain. A floodplain can either be an erosional floodplain or a depositional floodplain. And what that basically means is when the river gets too much water, much more water than it normally has, that water's got to go somewhere. That water is going to flood out, and it's going to be able to erode and pull all the soil and everything that's there. But eventually when the floodwaters recede, what's going to happen? The water is going to go back, but it's going to deposit the sediment that it was carrying from upstream. And so you're going to get some water, some dirt and stuff taken down initially during the flood, but afterwards you're going to get a deposit of a large amount of sediment. Okay, and there's lots of cultures that understand this. You guys did all this stuff when you did like the Egyptian culture and the Mesopotamians, understanding the flood cycles of the Nile and the Tigris and the Euphrates is very important. Another factor of wide valleys are what we call meanders, and meanders are basically the turns, the curves in a river. A young river tends to be very straight, a little bit of wiggle, but not too much. But as rivers get older, they tend to turn. Why? Because we talked about this last time. You're going to start to get places where you get a lot of erosion and places where you get less erosion and more deposition. And so the river itself is going to kind of move around. Okay. Sometimes this can get so extreme that you can actually get these meanders that get cut off and form into these weird little lakes that we call oxbows. Okay. If you're looking at the picture in front of you right now, you see a stream that's meandering, okay? And you can see that in this picture, you've got two colors. You've got the red and the yellow. The red are the places where you're going to get lots of erosion, and the yellow is where you're going to get lots of deposition. Well, as the river goes through time, you can see that the red mark in the upper left-hand side and the red mark in the lower left-hand side are growing and getting closer and closer to each other. Why? That means the river is literally eating away at the ground there, okay? And so what will eventually happen is those two chunks of the river will meet, and the water is going to take the path of least resistance and flow through there. But what that's going to happen is the deposition will actually do the opposite, and it will close off this loop. And so what you end up with is this horseshoe-shaped lake that we call an Oxbow Lake. And you see those quite often in very old rivers. Okay? For example, the picture you see in front of you now. That is what we call an Oxbow Lake. That horseshoe shaped used to be part of the river in front of it, but it got cut off. Why? Because there was deposition that happened between the original river path and that meander, and so it got cut off. Now, this is incredibly important. Why? Because when you're building houses or property, you need to look at the river and see how it's moving and how it's eroding. That picture that you see in front of you right now is a diagram of a river. The actual river is also in the picture, and what you can see is that it is eating away at one point and depositing at another point. That's where we talked about the cut banks and the point bars. That was in the lesson yesterday. Well, if you look at that house is not sitting on a good place. That house is sitting on a cut bank, which is an area where you're getting a lot of weathering and a lot of erosion. That house is in serious danger of one day ending up in the river. So it's incredibly important when we're building things that we understand this. All right, guys. So that does it for stream erosion and stream characteristics for today. Tomorrow we will be finishing up with streams erosion and beach erosion. So make sure that you guys are paying attention. Hope everybody's safe. Hope everybody's happy. And see you guys later. All right. Bye.